Good afternoon. Today we're going to be talking about section 4.5, optimization problems. And I have borrowed some information from a different textbook, but the majority of this content does come from your textbook that you can access online through MyLab Math. So here's an example of an optimization problem. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fencing along the river. What are the dimensions of the field that has the largest area? So in order to get a feeling for what's happening in this problem, let's consider a few cases. The figures at the bottom of this picture show three possible ways of laying out the 2,400 feet of fencing. And we can see that when it's wide and skinny and tall and narrow, we don't get a whole lot of area, but somewhere in the middle, we get something that's a really good combination of the two. So how do we use calculus to figure out exactly what it is we're doing? First, we're going to let x be the height of the rectangle and y be the width. And we can express the area, A, in terms of x and y. And this is just area equals length times width, and for a general case. However, in order to maximize the area, we want to express A as a function of one variable. To do this, we use the given information that the total length of fencing is 2,400 feet. That is, 2 lengths of x plus a length of y has to equal 2,400. So we can use that to rearrange. So 2x plus y equals 2,400 can be rearranged to be y equals 2,400 minus 2x. So we can plug this into our equation for area. So x times y becomes 2,400x minus 2x squared. And then we have to ask ourselves, well, what are some valid inputs for x, and how exactly do we maximize A? Now, we definitely can't put in negative numbers because we can't have negative length. So a lower bound is going to be 0. And if we plug in 1,200 feet for x, then we also get that area equals 0, right? So we can't have a length of 1,200. So we're looking for answers between 0 and 1,200 that maximize the area A. And then here comes the big question, how exactly do we maximize A? Well, we can do this using calculus. We can take the derivative, find where it's 0, and then determine whether it's, and compare it with the endpoints and see exactly what we do. So let's go ahead and take the derivative, I believe. And now all we need to do is set this equal to 0. So A prime equals 2,400 minus 4x. And we're going to set this equal to 0 and solve for x equals 2,400 divided by 4, which I believe is 600. So 600 is a critical point for A. Now we need to test the endpoints. Well, we already said that when we plug in 0, we get 0. And when we plug in 1,200, we also get 0. So the only thing left to do is to plug in x equals 600. And we get an area of 7,200,000 feet. And that's going to be our maximum. So that's exactly how we find our maximum. We're just using calculus to solve word problems, pretty much. So how do we talk about optimization problems? And this is probably what's going to trip you up the most. Not necessarily what is going on calculus-wise, but being able to talk about it using the terms constraint and objective function. So from the textbook, a constraint, well, let's start with objective function. An objective function is what we want to maximize. And a constraint is exactly that. It's constraining us. So maybe we only have 2,400 feet of fence. Maybe we've only got so much volume or so much money to spend at the grocery store. So then the question is, well, what was the objective function in the previous example? And the objective function is exactly that, what we want to maximize. And we want to maximize area. So area equals 2,400x minus 2x squared. That's what we want to maximize. Or A equals x times y. That's what we want to maximize. And what the constraint in the previous example is that we only have 2,400 feet of fencing. So 2x plus 1y equals 2,400. So now let's do some more examples so that you can get a little bit more familiar with what exactly is going on. This one, so think about pairs of non-negative real numbers, x and y, between 0 and 20, with the property that their sum is 20, and of all possible pairs, which has the greatest product. So what's the objective function? Well, we want to maximize the product. So I'm going to call that P equals x, y. And my constraint here is that x plus y equals 20, and that x and y are non-negative. So they're greater than or equal to 0. But we can already see from our objective function that if either x or y equals 0, we're going to get a product of 0. So x and y just have to be greater than 0. Our first step is to use the constraint to express the objective function in terms of a single variable. So again, our constraint here is x plus y equals 20, or y equals 20 minus x, and we're going to plug that in to our objective function, which is p equals xy. So I get p equals x times 20 minus x. That's going to be 20x minus x squared. Now I've got my objective function in terms of a single variable. Now that it's in terms of a single variable, what do we have to do? We have to find the critical points. So we take the first derivative, p prime of x is going to be 20 minus 2x, and we find the critical points. Now, if x equals 10, so let's think about our endpoints, right? If x equals sorry, I got ahead of myself here. So before we find critical points, let's talk about endpoints. If I plug in x equals 20, I get 0. And if I plug in x equals 0, I get 0. So I'm looking for answers in between 0 and 20. So now I can take the first derivative, p prime of x equals 20 minus 2x. And I've got two endpoints, 0 and 20, and one critical point. And I need to find that critical point by setting this equation equal to 0. So this suggests that x equals 10. So when I plug zero in, my product equals 0, When I plug 20 in, my product also equals 0. But when I plug 10 in, my product equals 200 minus 100, which is just 100. So here, x has to equal 10, y has to equal 10. And when we do that, we get a maximum product of 100. And we easily could have solved this by creating a table, but we're not going to be able to create a table for every example. So it's good to be able to use this using calculus. So let's keep going with more examples. So a rancher has 400 feet of fencing for constructing a rectangular corral. One side of the corral will be formed by a barn and requires no fencing. 3 exterior fences and 2 interior fences partition the corral into 3 rectangular regions. What are the dimensions of the corral that maximize the enclosed area, and what is the area of the corral? So here it's going to be really helpful to draw a picture. I've got my barn on one side, which means I don't need any fencing along this black line, and then I've got 1, 2, 3 exterior points, 3 exterior lengths of fencing, and 2 interior lengths of fencing. So I have one big corral with 3 baby corrals inside. So this is going to lead us to being able to write down our objective function, which is that same one, area equals x times y, and my constraint, which is I've got 400 feet of fencing times 1, 2, 3, 4 lengths of x and 1 length of y. Now I use my constraint to put the objective function in terms of one variable. And I can do this in either x or in y, it really doesn't matter. So this time, let's do it with rewriting what y equals. Y is going to equal 400 minus 4x. Our objective function a becomes 400x minus 4x squared. And let's talk about the bounds of this problem one more time, right? If I plug in x equals 0, I get 0, and if I plug in x equals 100, I also get 0. So I'm looking for values in between 0 and 100. So now we go ahead and we find our critical points by finding the derivative of a prime of x is equal to 400 minus 8x. We set this equal to 0, and we solve for x. X is going to equal 400 divided by 8, which is going to be 50. Now, we can almost skip this step where we test the endpoints because we know that when we plug them into our original function, we get 0. So really all we have to do is plug in x equals 50 and make sure that we get an answer that makes sense. And when we plug in x equals 50, our area equals 10,000 square feet. So x equals 50 implies that the area equals 10,000 square feet. And now that we have this answer, we just want to make sure that we're answering the question. The optimal length of the corral, that is y, equals 200 feet. So the dimensions of the corral are 200 feet by 50 feet, and the area is 10,000 feet squared. And that's our answer. I believe I've got 1 or 2 more examples left, so hopefully we'll wrap this up pretty quickly. Oh, didn't need that slide after all. Yes. So suppose an airline policy states that all baggage must be box-shaped with the sum of length, width, and height not exceeding 64 inches. What are the dimensions and volume of a square-based box with the greatest volume under these conditions? What are the constraint and objective functions? So first we draw a picture. Now this is a box with a square base. That means instead of length, width, height, we have width times width to create the base of the box. So we know our objective function is volume. Equals height times width squared, and we want to maximize that. And our constraint is that 2 times the width plus the height can't exceed 64 inches. So now, just like before, we use the constraint to express the objective function in terms of one variable. So we go h equals 64 inches minus 2w, and we plug that into our volume equation. Volume becomes 64w squared minus 2w cubed. I'll write that again on our next slide. Volume equals 64w squared minus 2w cubed. And we proceed just like we did last time by taking the derivative. Oh, I'm sorry. This should be a 6. I promise I can do math. So we found the derivative, and now we're looking for critical points. So we set this derivative equal to 0. We can factor out a w, and we get 128 minus 6w equals 0. Now this occurs at 2 places. This statement is true at 2 places. When w equals 0, this statement is true, but that's not very useful. So we're looking for w not equal to 0. So we set 128 minus 6w equal to 0, and we solve for w. W is going to equal 128 divided by 6, which is exactly 64 divided by 3. By the first or the second derivative test, we can say that w equals 64 over 3 corresponds to a local maximum, and the endpoints, v equals 0 and v equals 32, equals 0. Therefore, the volume function has an absolute maximum when w equals 64 over 3. It implies that our maximum volume is approximately 9,709 inches cubed. And the dimensions of the optimal box are w equals 64 over 3 and h equals 64 over 3, which you might be surprised just means the optimal box is a cube. We get the most volume for what we're looking for. So again, I have an extra slide, but here's how to proceed with optimization problems. 1, identify the objective function and write it in terms of variables of the problem. 2, identify the constraint function or functions, there might be more than one, and write them in terms of the variables of the problem, right? So this is that w times h equals volume, and 2w plus h equals 64. Then, step 3, use the constraints to eliminate all but one independent variable in the objective function. 4 is determine the interval of interest of our variable, so what's the maximum value we can plug in and what's the minimum value we can plug in. And then 5 is find the absolute minimum or maximum values in the objective function on the interval of interest. And it's really just as easy as that. So if you get stuck on any of the homeworks, just let me know and I'll be happy to help.